You've seen it everywhere. You rely on it every single second. But have you ever stopped to think, what actually is light? I mean, seriously. It's in your phone screen, in the sun, in fireflies, and even in those annoying billboards that blind you at night. But light isn't just brightness. It's one of the weirdest, most fascinating things in the universe. For one, it's a wave and a particle at the same time. Yeah, we'll get to that weirdness later. It's fast, really fast. In fact, nothing in the universe moves faster than light. If you tried to race a beam of light, you'd lose so badly that your opponent would be millions of kilometers ahead before you even blink. Light travels at almost 300 million meters per second. To put that into perspective, sunlight takes only 8 minutes to reach Earth from the sun. Light isn't just one thing. There's a whole spectrum of it, and we can only see a tiny sliver. The rest? It's invisible, but it's everywhere, buzzing through space, heating up your microwave dinner, and even making your Wi-Fi work. Radio waves let us hear music. Infrared keeps our pizzas warm. Ultraviolet rays give us sunburns. And gamma rays? Well, they're basically space lasers from exploding stars. But what is light made of? And why can we only see certain colors? Why do rainbows exist? And how does your eye turn these waves into, well, everything you see? Light can bounce, bend, spread, or even disappear into objects. And the way it interacts with things is what makes mirrors reflect glass-bend images and black clothes heat up in the sun. Without light, our world would be completely different. No colors, no shadows, no sunsets, just darkness. But don't worry, we have plenty of light. In fact, right now, trillions of photons are hitting your eyes, letting you see this very moment. And the strangest part? When you look at a star at night, the light hitting your eyes left that star millions of years ago. So you're actually seeing the past. Strap in, because today, we're breaking down light in a way you've never seen before. So, what exactly is light? At first glance, light seems simple, just the stuff that helps us see, right? But the more we study it, the weirder it gets. Light isn't made of stuff, like rocks or water. It's made of energy. It's part of something called the electromagnetic spectrum, a massive range of waves that includes everything from radio signals to gamma rays. Light is actually a wave of electric and magnetic fields moving through space. Picture a ripple in a pond, but instead of water, it's space itself vibrating. That's light. It doesn't need air or any material to travel through. It moves just fine through the vacuum of space. That's how we can see stars from trillions of kilometers away. Light simply brings us the past. But here's where it gets strange. Light is also made of tiny packets of energy called photons. They don't have mass. They don't even exist in the normal sense until they interact with something, like your eye. It's like they're traveling through the universe as potential and only become real when they hit something. Light is a wave and a particle. How cool is that? This is called wave-particle duality, and it's one of the strangest truths in physics. We have experiments that prove light behaves like a wave, interference, diffraction, and others that prove it behaves like a particle, photoelectric effect. The universe says, why not both? And then there's the speed. Light always moves at the same speed in a vacuum, about 300 million meters per second. That's almost 300,000 kilometers per second. Nothing with mass can go faster than this. It's the cosmic speed limit, and it shapes how we experience time and distance. Long wavelengths equals low energy radio. Short wavelengths equals high energy, gamma rays. Only a tiny range in the middle, called the visible spectrum, can be seen by the human eye. Imagine if you could see all wavelengths. Your world would look completely different. Wi-Fi signals, remote controls, even heat from your hand, they'd all be visible. So, to sum it up, light is a massless, dual-natured energy packet that moves at the universe's speed limit, doesn't need a medium, and lets you see everything, while hiding most of itself. Pretty wild, right? Alright, so now we know that visible light is just a tiny slice of the electromagnetic spectrum. But here's something weird. White light doesn't actually exist. What we call white light is actually a mix of all the colors of the rainbow. You don't believe me? Let's do an experiment. If you take a prism, a transparent triangular block, and shine a beam of white light through it, something amazing happens. The light bends and splits into different colors: red, orange, yellow, green, green, blue, and violet, just like magic, except it's science. This happens because different colors of light travel at slightly different speeds when passing through materials like glass or water. Red light bends the least, and violet bends the most. That's why we see them spread out in that exact order. Now, nature has its own version of this experiment: rainbows. Ever wondered how they actually form? It's basically a giant prism in the sky. When sunlight hits a raindrop, it enters, bends, or refracts, then bounces off the back of the droplet, reflection, and finally bends again as it exits. This entire process splits the light into colors, just like the prism. Multiply this by millions of tiny raindrops, and you get a full rainbow across the sky. But here's a fun fact: rainbows aren't actually arcs. They're full circles. You just don't see the bottom part because the ground gets in the way. If you're lucky enough to be in an airplane at the right angle, you can actually see a full circular rainbow. Now, not all rainbows are the same. Some are double rainbows, where a second fainter rainbow appears above the first one, but flipped. This happens because the light reflects twice inside the raindrop. And then there are moonbows. Yep, rainbows made by moonlight. They're rare, but you can spot them on clear, rainy nights. And if that wasn't cool enough, there are even supernumerary rainbows, extra, faint rainbows stacked inside the main one, caused by light waves interfering with each other. Science never stops being weird. And if you ever want to see tons of rainbows, visit places like Hawaii or Iceland, where the climate creates the perfect conditions for them almost every day. So, next time you see a rainbow, remember, you're not just looking at pretty colors, you're witnessing the hidden physics of light in action. So, what actually happens when light hits something? Well, light doesn't just stop, it interacts. And depending on the surface, light can do 4 different things: reflect, refract, diffract, or get absorbed. Let's break them down. Reflection: the reason you see anything at all. Imagine you're looking at yourself in a mirror. What's happening? Light is bouncing off your face, hitting the mirror and bouncing back into your eyes. That's reflection. But here's the interesting part. Not all surfaces reflect light the same way. Smooth surfaces, like mirrors or calm water, reflect light in a straight, predictable way. This is called specular reflection. That's why mirrors give you a clear image. Rough surfaces, like walls, paper, or your skin, scatter light in many directions. This is called diffuse reflection. That's why you can see objects clearly, but they don't act like mirrors. Without reflection, you wouldn't be able to see anything. Your eyes literally depend on light bouncing off things. Now, let's take reflection to another level. Echoes, but for light. Have you ever seen an infinite mirror illusion where mirrors reflect each other endlessly? That's light bouncing back and forth until it eventually fades. Refraction. Why things look weird in water. Okay, have you ever put a spoon in a glass of water and noticed how it looks broken? That's because of refraction. Refraction happens when light changes speed as it moves from one material to another, like from air to water or from air to glass. Since light bends at different angles, objects look distorted. This is also why lenses work. Your glasses, magnifying glasses, and even your eyeballs use refraction to focus light. No refraction, no clear vision. Oh, and refraction is also responsible for mirages in deserts. The hot air near the ground bends light, making it look like there's water on the road. But no, it's just a trick of the light. Here's another cool example. Diamonds sparkle because of refraction. Light enters the diamond, slows down, bends, bounces around inside, and finally exits, creating that dazzling effect. Diffraction: how light sneaks around corners. Okay, let's get weird. If light usually travels in straight lines, how can it bend around tiny obstacles? That's diffraction. It happens when light waves pass through small openings or around edges and start to spread out. A great example? CDs and soap bubbles. The rainbow colors you see aren't from pigments, they're caused by diffraction, as light waves interfere with each other in cool ways. Diffraction is also why we can hear people talking around a corner but can't see them. Sound waves diffract more than light because they have much longer wavelengths. And fun fact, this principle is what makes holograms possible. Absorption. Why black clothes feel hotter. Finally, let's talk about absorption. When light hits an object, some of it gets absorbed instead of bouncing back. The more light an object absorbs, the darker it looks. Black objects absorb almost all light, which is why wearing black on a hot day feels terrible. White objects reflect most light, which is why they stay cooler. Colored objects absorb some wavelengths and reflect others. A red apple looks red because it absorbs every other color except red, which bounces into your eyes. Absorption is also how solar panels work. They trap sunlight and turn it into electricity. But did you know that light absorption affects affects space travel? Satellites and spacecraft have to be coated in special materials to control how much sunlight they absorb, or they'd overheat in space. So why does this all matter? Because without reflection, refraction, diffraction, and absorption, the world would look completely different. No mirrors, no rainbows, no glasses, no colors, no cool visual effects. In short, light is pretty awesome. Alright, so we know that light carries different colors, but how do our eyes turn that into what we actually see? Let's break it down. Step 1. Light enters the eye. Imagine you're looking at a red apple. Light from the sun or a lamp hits the apple, and only red light bounces back. That red light enters your eye through a small opening, the pupil. The pupil controls how much light gets in. In bright environments, it shrinks to avoid too much light. In the dark, it expands like a camera lens, letting in more light so you can see better. Step 2. The lens focuses light. Once the light enters, it passes through the lens inside your eye. The lens bends and focuses the light onto the retina, a thin layer of cells at the back of your eyeball. Fun fact, the image projected on your retina is actually upside down. But don't worry, your brain flips it the right way. Imagine living in a world where your brain forgot to flip images. Weird, right? Step 3. The retina detects colors. This is where things get cool. Your retina is packed with millions of light-sensitive cells, two main types. Rods. These handle low-light vision and help you see in the dark. Cones. These detect color and work best in bright light. There are 3 types of cone cells, each tuned to a different color. Red cones detect long wavelengths. Green cones detect medium wavelengths. Blue cones detect short wavelengths. Everything you see is just a mix of signals from these 3 types of cones. For example, if only red cones activate, you see red. If both red and green cones activate, you see yellow. If all 3 activate, you see white. This is the same principle behind RGB screens. They mix red, green, and blue pixels to create all the colors you see on TVs and phones. Step 4. Your brain puts everything together. The retina sends all this information to your brain through the optic nerve, where your visual cortex processes it into the image you recognize. And here's something wild. Your brain actually fills in missing details. There's a tiny blind spot in your vision where the optic nerve connects to the eye, but you never notice it because your brain auto-corrects reality. So, in short, light enters, gets focused, hits special color detecting cells, and your brain does the rest. That's how you see the world. So, let's take a moment to appreciate how mind-blowingly cool light is. It's everywhere. In the sun, in fireflies, in your screen, and even in deep space. It moves at the fastest speed in the universe. It acts like a wave, but also like a particle. It bends, bounces, splits, and gets absorbed. And without it, we wouldn't see a thing. Let's recap what we've learned today. White light isn't actually white. It's made of all colors. Reflection helps us see and makes mirrors work. Refraction bends light, making objects look distorted and creates rainbows. Diffraction lets light sneak around corners and create cool visual effects. Absorption explains why black clothes feel like portable ovens. Our eyes use cones and rods to turn light into the images we see. But here's the mind-blowing part. There's so much light we can't see. The visible spectrum is just a tiny sliver of the electromagnetic spectrum. If you had supervision and could see radio waves, you'd watch Wi-Fi signals dancing around you. If you could see infrared, every warm object, even your pet, would glow. And if you could see ultraviolet, the world would look completely alien. In a way, our reality is limited by our eyes. There's a hidden universe of light waves buzzing around us, invisible but always there. So, next time you see a rainbow, use a mirror, or wonder why dark clothes make you regret your fashion choices in the summer. You'll know exactly what's happening. But science isn't just about knowing facts, it's about asking new questions. For example, if light is the fastest thing in the universe, what would happen if we could travel at its speed? What if we could see X-rays? Would hospitals look terrifying? And what would the world look like to a species that sees in ultraviolet? Drop a comment below with your favorite light-related fact. And, as always, stay curious.